Simplified. I'm back to where we left off in our lectures on titrations and buffers. We begin titrations, and we saw the experimental procedure and the equational procedure that represents titration pH equals to pKa in our last class. So this morning, today, we're going to continue on titration and buffers, and we're going to start off with the titration curve. So we'll start off with the titration curve. A titration curve. All right, so what's a titration curve? A titration curve is a plot of the pH on the y-axis versus amount of OH added on the x-axis. Okay, so I'll just take that simple definition down quickly. A titration curve is a plot of pH. It's a plot of pH on the y-axis. Okay, graphical representation versus the amount of OH minus added, which represents the base added, and that's what on the x-axis. On the x-axis. So below, we'll quickly look at how the titration curve looks like. Okay, so titration is about the uh, mixture of acid and base to form water. Okay, so you have your acidic solution, which is usually a pH of less than 7, and you begin to add your OH minus that represents your base to it. That's simply what titration is. And when you add this OH minus representing your base, the pH will begin to increase from acidic solution, and as it continues to increase, it gets to a point where every single bit of the acid represented by the H plus have been ripped off by the OH minus, the base that is being added to produce water, more like a neutralization reaction. And what you have is a diagram that looks like this. So you have your, sorry. Okay, so you have something like this on the y-axis. Then you have the x-axis on the horizontal part looking like this. So your y-axis, like we said, is your pH scale. The y-axis is your pH scale, and you have your x-axis as your amount of OH added, and this is in mil. So you have your pH scale. Let's say this is the 0 mark, and you have 1, 2, 3, 4, 5, 6, 7. So let's say we have a pH of 7 around this point: 8, 9, 10, 11, 12, 13, 14. So you have pH neutrality point of 7, and you have acidic point below, and alkalinic point or basicity above. So this is how your pH look like, the pH titration curve. So as you continue to add your OH representing the base to the acidic solution, the pH begins to rise from the acidic medium. Okay, so it begins to rise from the acidic medium something like this. So sorry, let me just draw that again. Let me do that sketch again. Okay, so say the pH begins to rise from the acidic medium following a path, okay, something like that, that looks like that. So as you add your OH, drops of OH in mist down this path, you get to a point where where you have the you have all the OH has ripped off the hydrogen ion concentration in the acidic solution. Okay, and half that uh, concentration of the OH is referred to as the half equivalence point. So somewhere around the middle here, you have the half. So you have your half equivalence point. Let me do this in red. So right here you have your half equivalence. And this half equivalence implies when you have just enough OH minus concentration representing the base has been has been added to convert half of the acid, half the amount of the acid, half the amount of the acid to its conjugate base. Good. So that's what the half equivalence point is about. Just enough hydroxy ion concentration has been added to convert half of the acid to its conjugate base. All right. So you have at this half the mark, tracing it up here. Okay. So they have the mark is actually, sorry about that. So that's actually have the mark. So I'll redirect this arrow. Okay, so it's at this point that you have the equivalence right here, half equivalence. So at that half equivalence, you can actually trace this point to the pH scale. Okay, so let me do that in red again. So if we trace this to the pH scale, this particular mark here is actually referred to as your pH is equal to pKa as established in our last lectures. Okay, then you have where you have your maximum. I'll take my blue pen again. Here you have your maximum coming down Okay. So let me. Good. So this point here that traces down right here appears to be the maximum amount of your OH that is added. And when it is traced here, you will see that it's actually above the equivalence point. All right. So, but this point where you have this traced down to your x-axis where you have OH minus added, this point is referred to as this point right here is referred to as your equivalence point. Your equivalence point. All right. So this is this equivalent point is when just enough. This is the point when just sorry about my pen. When just enough OH minus has been added, when just enough OH minus has been added to react with any to react with any and all all H plus present in solution and all H plus present in solution. But however, you will notice that this equivalent point, when you trace it to the curve and you trace it to your pH scale, you will observe that it's far above pH 7, which we say pH is what? A point of neutrality. Okay, so it's far above it. Yes, at equivalence. So at equivalence, you have your pH equals to pKa. At equivalence, you have your pH is equal to pKa, and that point is exactly when you have enough OH minus has been added to convert half of the acid solution to its conjugate base. That is the half equivalence point. And the equivalent point is just when you have enough hydrogen ion concentration that has been added to rip off or accept all the proton, which is your H plus, that is present in solution. Okay, so if you notice, one would think that at this equivalence point it will be equal to pH 7, but it's not so, because we expect a pH equal to 7, but since we are titrating a weak acid against the base, we now have another reaction that takes place as follows. I'll do that in the next page. Okay, and that reaction, when it takes place, all of the um, conjugate base is now in the solution, but the conjugate base that is in solution of the weak acid, we have to now react with water to form what is called a new equilibrium. So we'll see that in the next page. Right here in the next page, I'll just like to put that down. Notice, notice that at equivalence, notice that at equivalence, we actually expect a pH equals 7, but since we are titrating a weak acid, we now have another reaction. We now have another reaction that takes place as follows. So we have another reaction that takes place in which the conjugate base that is formed in the solution when we titrated a weak acid, okay, and the conjugate base that takes place in the reaction now reacts with water, and what that gives you is a new equilibrium. So this is our conjugate base of acetic acid, as we had seen previously, plus water, and that forms a new equilibrium, forming back your weak acid plus your OH minus. Alright, so this OH minus is this new equilibrium that is formed. This reaction here now forms what? A new equilibrium. And this new equilibrium that is formed releases the OH into the solution. And because the OH is released into the solution again, thus the pH is far greater than 7, because that will further increase the alkalinity of the system once it comes to what? A new equilibrium. So what we see right here in summary is that from the graph we saw in the previous page, we saw that in pH at equivalent point is far higher than the neutral point, and that is because a new equilibrium a new equilibrium a new equilibrium is formed and that new equilibrium actually releases the OH out into the solution again, thereby increasing the basicity. And that is why at equivalence point you have a higher pH as seen in the graph previously. So this releases, this new equilibrium releases, this new equilibrium releases the OH minus, into the solution, thus pH is what? Greater than 7. Once the system, thus pH is greater than 7 once the system, sorry, let me separate that a little bit. Thus pH is greater than 7 once the system comes to a new equilibrium, Yes, that's basically it. So from the illustrative diagram we previously had, when a certain amount of OH minus have been added, you have what you call the equivalent point. And it is when this equivalence point, it is just when there is enough OH minus that has been added to react with any and all the H plus present in solution, whether the H plus is floating around in solution or is being ripped off from off an acid. So in this case, there are certain amount of H plus in acetic acid, which is our weak acid example that we are looking at. So when OH minus, which represents the base, is continuously added in succession, it successfully converts the H plus to water to neutralize it. Now completely, now we have completely in solution acetate, which is what your ACO minus that is left in solution floating around, just the acetate and the water. Then you have the half equivalence point, and this half equivalence point is when just enough OH minus has been added to convert half of the acid to its conjugate base. And in the titration curve again, we also saw pH is equal to pKa. So what is happening here is that I try to do a titration curve with each little bit of the OH minus, or the base, that's OH minus representing the base that is added. The pH is red, and the pHs that is red can now be used to plot a graph in which you find the half equivalence point, and it it is read from the psk of the graph, and that automatically gives the pka, as pH is equal to what? Pka. So notice something else in the graph that we saw, that at pH 7 is a point of what? Neutrality. So if I take a strong acid and I take a strong base, say hydrochloric acid and sodium hydroxide, if I neutralize the and hydrochloric acid, which is your HCl, with the base, okay, at equivalence, the pH is going to be 7. Notice in this particular case, the pH is not 7, it is actually above 7, and that is because a weak acid is being titrated. So when a weak acid is titrated with a strong base, all of the acid is eventually converted to acetate using acetic acid as our weak acid example. Now you would think that the pH will be 7, but for a microsecond it is 7, but something else happens almost immediately. Since we are titrating a weak acid, another reaction takes place. This is because at equivalence, we have converted all of the acid to acetate. Now there is no more acetic acid, all of the acid is being neutralized, and there is no free floating acid as represented by H plus, as all of them has been ripped off, and all we now have in solution is what? The acetate. Thus it is all of this acetate now, which is the conjugate base of a weak acid, that will now react with the water that is floating around in, as seen in this equation right here, as seen in this equation right here. So as such, the system comes to a new equilibrium. So if I have the acetic acid solution, if I titrate it, and if I have just enough OH minus, that's the base, to convert all of the original acetic acid to acetate, at that microsecond the pH is going to be 7. Everything is neutral. But now that I have acetate floating around, remember that acetate is a weak acid. Acetic acid is a weak acid. It has a very small pKa, which means it does not want to be acetate. It wants to be acetic acid, not acetate. Therefore, if there is ACO minus and is floating around, it is going to do everything it can to pull a hydrogen ion from any source that is available to become what? Acetic acid. Now the only other source of H plus in solution is what? The water in which the acetate is floating around in. It actually now rips off the hydrogen ion away from the water, producing OH minus indirectly. This OH minus concentration actually goes up, and that is why the pH is bigger than 7, thus creating a basic solution once the system comes to what? A new equilibrium. And this happens instantaneously. We don't see it, but it's happening, converting the acid to acetate, and the acetate reacting with the water to form um, acetic acid again, and what? OH minus, that eventually increases the basicity of the solution. So that's all we take for the titration curve. In our next set of lectures, we begin to look at buffers.